think it could happen here in Keokuk, but
Some sort of take it three situation.
Right? I don't know who you are, but I will find you. And I'll get my glasses back.
okay. So we're skipping 9 and 10 for now, and going on to. Wait a minute.
Are we ever going back to Department 6? Wait, I don't know.
We did. I think we did do that one. So we're gone to 11, and then actually 12. 11. We should knock out 11 today. My laptop is so powered up, you guys. It's not even funny. I plugged in last night.
6% left.
No. So we should be good that way. So we'll knock out this part, and then part 12 is actually, we need to get to that before your lab on Thursday, because you're going to be looking at freezing point depressions, and that's 12.
Oh.
So every year, every semester, this is where I am. I'm kind of skipping around a little bit. So we're going to look at Raoults law, which Raoults law actually, remember when we talked about making a solution where you took the solvent and you took the solute and you had to break the bonds, okay, took energy, and then as new bonds were formed, when they got together, then energy was released, and we kind of looked at that overall energy. We talked about ideal solution is basically one that obeys Raoults law, or will obey Raoults law. An ideal solution is the energy required to break is equal to the energy that is released when they form. That's an ideal solution. We're going to actually see this coming up here in a minute. But colligative properties, what is this slide about? Colligative properties are so cool. So you know how sugar tastes sweet and salt is salty and, sand you wouldn't want to eat. So those are kind of properties of those things. I know, but a colligative property doesn't depend on what it is. It just depends on how much you have. It is so cool, okay? And the colligative properties we're going to look at is freezing point depression and boiling point elevation. Colligative, it just depends on the particles basically running interference. That's the way I think of it. I don't care what they are, okay? So, vapor pressure lowering. So if you want to boil, how does this go? If you want to boil something to cook at an upper elevation, do you guys know what you do to the water? You add salt to it, yes. And the reason you add salt to it is to actually make it boil at a higher temperature than it would have otherwise boiled at. Because when you climb a mountain, your pressure is less and it's going to boil at a lower temperature. So you add salt to kind of compensate for that. Okay? So vapor pressure lowering. When you add salt, basically, you are lowering the equilibrium vapor pressure of that water. The presence of a non-volatile solute, being your salt, will cause the vapor pressure of the solvent to be lower than it otherwise was. So here we are looking at a video, which should work. Let's see. I think I linked it last night fine. Come on, play. Please. And you know you want to play. Well, come on, baby. 14 MO7. Now it's really mad. All right.
When a non-volatile solute is added to a liquid, some of its molecules occupy surface sites in the liquid, displacing volatile solvent molecules. Because fewer solvent molecules get to the surface, fewer can escape, and the vapor pressure of the solution decreases.
Can you see what I mean by they run interference, kind of? Okay. Now make sure we're all on the same page. Non-volatile means that it doesn't, it doesn't go into its gas phase. Non-volatile. So salt definitely is one of those. So we're talking about a non-volatile solute added to something that has a little bit of volatility to it, and water has a little bit of volatility to it. All right. Okay, so these look like pressure, temperature, phase diagrams. Good. There's a couple superimposed on. You kind of see the three sectors. Okay, the three sectors go like this. We have solid, liquid, and of course we have gas down there. Now the reason there are two is one is the pure stuff. The blue is the pure stuff, and the pink is the stuff that's been, we call adulterated. The stuff that has had stuff added to it. So the pink is the stuff that has an extra non-volatile solute there. So can you see where, for instance, if we take an isobar that's at the same temperature, pressure, okay, we take the same pressure. Remember, the pink is the stuff with the solute in it. So this is pure, okay, and this is with a solute. Can you see where the boiling point temperature is increased? That's actually, we're going to call it affectionately BPE, boiling point elevation. We're going to talk about that. But aside from that, let's look at the vapor pressure lowering. Here we go. Let's take an isotherm. Let's take it right there. Okay, can you see where the pure stuff, okay, has a higher equilibrium vapor pressure than the stuff that has a solute added to it? Yep, so that's a lower EVP, equilibrium vapor pressure. Equilibrium vapor pressure lowering. And here on a slide coming up, we're actually going to call that, this right here is our delta P, our pressure lowering by adding a solute. All right, cool. So this is kind of looking at it more closely. It's kind of isolating the segment of the Y that, of course, this is a liquid and this is a gas or vapor. Okay. The red line here is the pure stuff. The blue line is the stuff to which a non-volatile solute has been added. Pure benzene, benzene with a solute. Again, it's a colligative property. Do I care what the solute is? No. Just that it's non-volatile. And here, actually, in the next part we're going to talk about, we care what the molality is. What's the symbol for molality? Lowercase m. We care what the molality is. Okay. Yep. So this is going to be your boiling point elevation. Okay. For the same pressure, it's going to boil at a higher temperature when you put salt in it. Okay. And then this right here is your vapor pressure lowering. So this right here, of course, delta means change in. Okay. So this right here is your delta P, your equilibrium vapor pressure lowering because you added a solute. Why did it do it? Because it kind of ran interference, created a lower equilibrium vapor pressure in the head space above the liquid is how I think of it. So what does the X stand for? What's that X is equal to 0.135 mean?
Mole fraction?
Yes, exactly. Mole fraction. So here in a minute we're going to talk about how Raoults' law looks at the mole fraction of, there's far too many S's, the mole fraction of, I think, first we're going to look at the solvent and then the solute. But anyway, all right. So we're kind of building up to Raoults' law. So sometimes a lot of this you're like, it's good background to know, to show you how we got Raoults' law. Anytime you see a knot, I kind of call that P knot. Think of that knot as the pure solvent, okay? Pure solvent. And without the knot, it's a solvent to which a solute has been added. So no knot means you're talking about solution, okay? All right. So it's always final minus initial whenever we do a delta, and we had a delta P there. So it's always final minus initial. Our initial is going to be our P naught, okay? Because it's what we started with. It's your pure stuff before you put non-volatile solute in it. And then without the naught, it's going to be our final condition. Am I going too fast? Okay. So deltas are always final minus initial. So in this case, it's going to be P, the equilibrium vapor pressure of the solvent to which a solute has been added, that's your with stuff in it, minus P naught. And that is your pure equilibrium vapor pressure. That's your delta P. Now the fact that it's got a blue box in here around it means that it's kind of an important equation. And I double checked, and yeah, this is definitely a unit where I'm going to give you equations on your Unit 2 exam, but you need to know how to use them. Okay? So, all right. Very good. So make sure we're all on the same page. That delta P is that little bit we kind of saw where the one curve was under the other curve. The curve on top was the pure stuff. The curve on the bottom was the stuff to which a solid, non-volatile solute had been added. The delta P is right there along that isotherm. So it's been a while since we used this infinity sign with a bite taken out of it. That's a proportionality symbol. So one of the things that we know is that, now this is the P naught. No, this isn't the P naught, so this is just the P. So what does that mean? Is it with the pure stuff or the not pure stuff? It's the not pure stuff, exactly. So all this is saying is that if I have a mixture, okay, where I have, I'll go ahead and make my volatile solvent circles, and I'll make my solute X's, okay? And I'm going to go ahead and make circles up here in their gaseous phase, okay? All this is saying is that the equilibrium vapor pressure of this one is related directly to the mole fraction that you have down here. Okay, makes sense. If you increase the mole fraction here, you should increase the equilibrium vapor pressure. Yeah. Well, we're going to take that proportionality symbol out and we're going to replace it with something. For now, we're going to throw in a K, kind of like we did with ideal gas law equation, and we're going to see what makes sense. So, if we recognize that if you have pure, check this out, I was thinking about this getting ready for this lecture. I'm going to make pure, oops, not X's, that's my non-volatile solute. I'm going to make pure dots down here, no X's, okay? And I'm going to close these off. Does this make sense that this actually is going to be, it's going to be back to our P naught because there's nothing in there. Does that make sense? Okay. And in this special case, the mole fraction of solvent, since it's pure, like the slide says, is 1. Does that make sense? All right. Well, we're getting close to being able to find out what our K is. If you make that 1, and I think this needs to go over, actually, this P naught should be under my K. As it turns out, our K is equal to the equilibrium vapor pressure as it's in its pure state. And that is one form of Raoults law. Blue box alert. Okay. So you'll see this equation, and you'll need to be able to kind of work with this equation. All it says is that if you have a mixture of a solvent with some solute dissolved in it, your that equilibrium vapor pressure is going to be equal to the mole fraction of the solvent times it was as it was pure. and I'm gonna put it this way, or emphasize this. This right here, pure, right? Guess what? You get that from a table, usually. Yeah, equilibrium vapor pressure at a particular temperature. Mole fraction of solvent, we can do that. All we gotta know is, you know, relatively speaking, you know, come up with a, no, do the trick. Mole fraction of solvent, you guys did some problems like this, is equal to moles of solvent divided by moles of solvent plus moles of solute. Right? So we can do that. So we talked about ideal solutions. An ideal solution, like I said, is the energy required to break those bonds for your solution to be formed is then, that energy required is energy that's released when those new bonds are formed. Okay. Another thing here is, and we're going to kind of, at the end of this part, I have an assignment slide coming up, and then we're going to do a few other examples where we have an extra component. We basically have, I'll go for here, and I'll make, what other symbol can I do? I'll do dashes like this. My dashes like that, actually, I know I've changed it up here, but is a second volatile substance. So not only do we have these here, but we also have these here, okay? And they're gonna follow Raoults law too. And like this says that even if your solution is not ideal, the energy is not equal, and it's either endothermic or exothermic for this creating a solution, it still works, generally
I
speaking.
like us as reasonably.
Reasonably.
Like, it works. We should probably consider using something else.
Yeah. Oh, when your scale up doesn't work, it's like, I guess that was a problem. Okay. Okay, mole fractions. The sum of the mole fractions is equal to 1. Did you buy that? Okay. So this is actually just kind of doing, showing Raoult's law twice. It works independently on component A and component B. So again, this is the partial pressure of A in the headspace above the mixture is equal to its mole fraction times what it was in its pure state. Partial pressure of B in a mixture is equal to the mole fraction of B times what it was in its pure state. And of course, Dalton's law of partial pressures, I guess, part of it is their additive. The total pressure is equal to the sum of the two individual pressures. Okay, so salt was the example I used for a non-volatile substance. And again, this is a colligative property. So this whole vapor pressure lowering does not depend on what the thing is you dissolve, but just that you dissolve something. And it matters how many how many particles you dissolved. And that's going to actually, we're going to get to molality is the way to describe that. So back to this one right here, where my X's were salt or something that's non-volatile, okay? Basically, all this is saying is that this is not going to go in your vapor phase. It's going to stay down here. And that's the one that I want to focus on, the non-volatile substance added to something that's relatively volatile. So, let's see if I want to make a picture that I can refer to. Too many S's, too many S's. You have your solvent, your solute, and your solution. Oh, are you serious? Okay, let's see what we got here. Looks like our solvent is water. And our, let's see, I'll start from the beginning. Calculate the vapor pressure of water. Okay, so I'm gonna go ahead and put a watch glass over here. This water is going to be in equilibrium, and these are my water gas particles. Here's my water liquid particles. I'm gonna say the temperature, like it said, is 90 with out to the nearest degrees Celsius. And it says we are going to add the solute, we don't care what it is, but we're gonna add 5.0, well, we do kind of care because we need to know the moles of this, 5.00 grams of C6H12O6. And we're going to add it to 100 with 4 sig figs grams of H2O. So the question is, what is the pressure, equilibrium pressure of H2O? So according to Raoults law, the equilibrium pressure of H2O is equal to the mole fraction of H2O times what H2O would be at that temperature. That's it. So it went ahead and looked up the table. I told you that this is the one you're going to get from the table. According to the table, that value is 525.8 millimeters of mercury. Okay, so we're looking for a reduced equilibrium vapor pressure, aren't we? Because those colligative property of the sugar, the glucose, exactly. So this is to kind of prove to you where that number came from, the 525.8 millimeters of mercury. Okay, but does this make sense? Raoult's law, I mean, that's pretty straightforward. So you can use whatever units, as long as you'll just end up with the same units. It doesn't have to be converted to atmospheres or anything. That's kind of nice. Unless the problem asks for it. So there's Raoult's law. And just to remind you what the mole fraction means, in this case we're going to take the moles of water divided by the moles of water plus the moles of glucose. That's it. So we kind of have some Gen Chem 1 kind of business to do here, taking those masses and getting moles. So the moles of water, we take that 100 grams, 100.0 grams over 1, times 1 mole over 18.02 grams, molar mass of H2O. So you're looking at 5.549 moles of H2O. Then we need the moles, that's the solvent. The moles of the solute look like this. There was 5 grams of glucose, and we take our C6H12O6 and we get 180.16 grams per mole. So 1 mole of 180.16 grams. Round to 3 significant figures, the moles of the solute is 0.0278 moles. So then on the next slide, what you're going to see is we take this number and put it here, and this number and put it right there. So it looks like this. Mole fraction of our solvent is 5.549 moles divided by the total moles. Total moles. 5.549 plus 0.0278. And it's going to be unitless. So we get our mole fraction of water is 0.9950. That's pretty high. So that's the number that we're gonna multiply by its, what it was in its pure, we're gonna multiply that by 525.8 to get what it would be in this situation. So here we go. Dun dun dun, drum roll. Could I have any more builds for that? Oh my goodness. So down there at the bottom finally is what we get now as the equilibrium vapor pressure of our solvent in our solution. So it's at 0.9950, that's the mole fraction of water in this particular situation. And the 525.8 millimeters of mercury, that's the equilibrium vapor pressure of water as it would be in its pure state at that temperature. Looks like 4 sig figs, that's a lot of sig figs. So I got an equilibrium vapor pressure of 523.2 millimeters of mercury. And I think I go on and go ahead and do that means my delta P, okay? So what was the change in equilibrium vapor pressure? That's delta P. And it's final minus initial. The final is the with the glucose, and the initial was without. So these are actually going to be negative. Your delta P should be negative. So delta P is what we got applying Raoults law, 523.2. Now notice I didn't do a lot of this in Chem 1, maybe a little bit. But if you have two things that have the same units, like these, what you can do is put the numbers in parentheses and then put the units outside if you're doing a difference. If you're doing a difference, that's kind of nice. So using Raoults law, we came up with 523.2. The pure from the table was the 525.8. And then, yeah, these should be negative, your delta P's. All right. Sigh. We've got time to finish the part, but let me take a look at these. 1353. There it is. Looks like that's not what it looks like. There it is. These are kind of fun, I think. So that was Raoults law. Let me see what hint I have. Okay. So use mass and molar mass to get to moles. Of course, you need moles to get to mole fraction, right? So it's very similar to what we did in lecture here. See, they give you what the literature value of the pure equilibrium vapor pressure of water is. So it's really not too bad. The next one is similar. Let's see. Oh, kind of. This one you have to kind of tease out the mole fraction is the problem. They go ahead and they say that the solvent is methanol, the solute is urea, and they give the formulas up there. Now, you guys okay with this? The fact that it's C, capital O, what does that stand for? Carbon and oxygen. It does not stand for cobalt, okay? Had some students kind of do that. But anyway, if you use as your basis 100 milliliters of methanol, since you're given the density, you can get to the mass of methanol. And then you can backtrack that to, well, you just can. I did. If I did it, you can do it. That kind of hurts my brain. I have to kind of doodle. It's very doable. And then once you get to the moles, kind of massaging it from volume and masses and density, then you're ready to knock out the mole fraction take its mole fraction times what it was in its pure state at this temperature to get the equilibrium vapor pressure of the solvent in the solution. Okay, here's one. It's a little different. It's kind of a look at it sort of thing. In this case, kind of picture a watch glass over, we could call the first, well, solution A and solution 1 and solution 2. Picture a watch glass over there and kind of picture the little water vapor particles going ahead and kind of filling the air region above it. What would you say about which of these, 1 or 2, has the greater mole fraction of water? How many people think 1 has a greater mole fraction of water? How many people think 2 has a greater mole fraction of water? Very good. Okay, so just looking at Raoults' law, then you can kind of gauge some things. I think you'll do fine. There's no calculations required for this one. Yay! Just kind of looking at it. So there's your hints for that one. The next one, is that it? Oh, that was it. Okay. Back to the show. No, we aren't. I changed my mind. I changed my mind back and forth so many times last night. And this is finally where I ended up. So we're going to finish knocking out part 11, and then this will work great. Wednesday we'll have time to do part 12, and we'll be fine to talk about the lab. All right, so now we're switching it up, and we are going to look at 2 volatile substances okay? And remember, we said kind of independently, they each volatile substance in a mixture of 2 volatile substances will follow Raoults' law. And this kind of goes back to a Chem 1 thing. We said that actually the total vapor pressure over the solution is the sum of the partial pressures. Right, no duh. Now, as I go ahead and you know, my husband and I kind of discuss strategy for what we're going to test you over. Actually, I'm not going to test you over 2 volatile components, but I want you to have a sense for how to work the problems. I will test you over 1 volatile component and a non-volatile solute that's been added to it. But let's take a look at some examples. First off, before we look at an example, if you have A and B and they're both volatile substances, the mole fraction of the sum of them is equal to 1. I'm sure you're good with that. Okay. And this actually is a slide we looked at before. Each one of them independently follow Raoults' law. So, yeah, I think we're okay with all that. Now, in order to work this one, I'm going to actually kind of put it over here on the board. I wish my slides were a little more, you know, they're usually pretty thorough, but I think they kind of miss a step, and it's kind of a straightforward step. But so we're going to look at a mixture of benzene and toluene. And sometimes, like, if I don't want to write the whole thing, I'll write a little key at the top. So I'm going to say benzene, I'm going to call that B, and toluene I'm going to call T. It just makes life easier. Now, you can't go off on a rush just doing things unless you say what it is. Okay? So it gives us, in the pure state, at this particular temperature, at 20 degrees Celsius, the P naught of benzene is 75 millimeters of mercury when it's pure, and when it's pure, toluene has an equilibrium vapor pressure of 22 millimeters of mercury, and this is at T is equal to 20 degrees Celsius. All right. Then that's not specific to the problem. What's specific to the problem is it says that the number of moles of benzene, so I'm going to put N of benzene is 1.0, and N of toluene is 2.0. So we have some questions we're going to answer, okay? In fact, I think this might help you later on problems that are due in the next assignment slide. I'm going to put number of moles of benzene, I'm going to put in its liquid state, number of moles of benzene, comma, L, okay, is equal to 1.0 moles. And I could put number of moles of toluene, T, comma, L, is equal to 2.0 moles. So these are the questions we can answer. What is the vapor pressure above the mixture for each substance? Well, we should be able to simply use that the pressure of any of the substance is equal to its mole fraction times it was in its pure state. That should be pretty, not too bad, right? Okay. What is the total vapor pressure? Well, all we got to do is add P sub T plus P sub B, right? Now my T's are kind of messed up because T is total, so I know. What is the mole fraction of each substance in the vapor phase? Now, in that last one, we're actually going to use, I'm pretty sure this is one of Dalton's laws, but we're going to say in its vapor pressure, what's the mole fraction? We're going to say that that for each of the components in its vapor phase, that partial pressure is equal to mole fraction of the component times the total pressure. I'll put TOT for total pressure. I'll introduce something else. It's kind of a different, it's not Raoult's law, it's something different. Well, let's take a look. This was where I wish, I don't show you where those 0.33 and the 0.67 come from, but let's just double check, make sure we're all on the same page. The mole fraction of benzene came from the 1.0 divided by 1.0 plus 2.0. Okay? The mole fraction of toluene came from the moles of toluene, which is 2.0, divided by 1.0 plus 2.0. That was the one thing I wished I had put on my slides. So,
What's the 0.67?
0.67, yep. Yeah, 2/3 is 0.6 repeating and 1/3 is 0.3 repeating, so, yep. So now we're ready to basically knock out the first question. I'll put both of these up here. So in its vapor phase, the equilibrium vapor pressure of the benzene will be equal to its mole fraction, 0.33, times it would be in its pure state, 75 millimeters of mercury. So you're looking at, in the headspace, I'll go ahead and put that P of B is equal to 25 millimeters mercury. And the toluene, we take its mole fraction, which was that 0.67, times it was in its pure state, 22 millimeters of mercury, and we get 15 millimeters of mercury. So we answered the question 1. Question 2, what's the total vapor pressure? Well, we just add them together. And that gives you your P sub TOT for total. Makes sense. And then the last one, what we're after is, what is the mole fraction of each one of these? And actually, the last one, I'm going to point to the vapor phase, the headspace, and I'm going to put mole fraction of toluene is equal to question mark, mole fraction. I'll put toluene comma G for gas, benzene, comma, G for gas, okay? Do you see what those are two different mole fractions? That's where it confuses me. Why are they different? Because you have different degrees of volatility. And then it kind of confuses me, I guess, because I figure if it evaporates, well, I guess the mole fraction in its liquid state changes, I think. But now we're looking at mole fraction in its gaseous state. So in its gaseous state, all we have to do, and I wish, I'm going to put a little TOT underneath that second P right here. The partial pressure of either component is equal to its mole fraction times the total pressure. Now, we know this one, we got that one. We know this one, and we're trying to find that one. Okay, so we can rearrange, be careful when you rearrange. We can rearrange that, and of course then get the mole fraction is equal to the partial pressure divided by the total pressure. I'll go ahead and make sure we're still on the same page. Up here, I could rearrange that, and I could say the mole fraction of component A is equal to its partial pressure divided by the total pressure. And that's exactly what I'm doing right here. The mole fraction of the benzene is equal to its partial pressure, which was 22 millimeters of mercury, divided by its total pressure, which was 40. So it's 0.63. And we can do a similar thing with the mole fraction of toluene in the vapor pressure, in the vapor state. By taking its partial pressure, which we came up with 15 millimeters of mercury divided by the total pressure, 40.40. So 2 sig figs 0.37. That's the mole fraction of vapor phase. I guess that's what bothers me, because it's like, well, if you're letting it reach equilibrium, then the mole fraction in your liquid has changed. Which is correct. All right then. Dun dun dun. So if you want to, go ahead and in getting ready, Joe, go ahead and put out, don't do 47, because we haven't talked about Henry's law of the solubility of gas in a solution, and I just think that one would be a hard one to do when we haven't talked about that one, you know? And this one, I'm actually going to give you a handout, because I know when I did it, when I did it in my notes, I'll give it to you now. I actually had to do it, or did it with 3 equations, 3 unknowns, and simultaneously solving them, and I know it hurt my brain. And there's probably an easier way, but that's how I did it. So this says 52, but it's really, I think, 56. So draw a line through that and put 56. So, you know, feel free to look at what I did, or come up with your own creative way. So there's 2 for sure I want you to do. How's that sound? Okay?
Was this extra credit then?
Yeah. Yeah, do it for extra credit. I like that. 10 extra credit points. Let's make it a whole assignment. So do 52 and 55, but you can't just take mine and do it verbatim. You'll have to like, now how did you, or you improve it. Take mine and improve it. You wouldn't take mine and just do it verbatim. Come on.
I think you're underestimating what I do for extra credit.
Yeah, this will be worth 10 extra credit points, but these do for sure for regular credit.
56 is worth 10 extra credit, not
Yeah.
56 and 47.
Right.
So we
Oh,
can-
do you want,
we can
no,
just
don't do 47.
We can just do 56 and not turn the assignment, still get the same credit.
You know what? You can shut up anytime, Mike. I'm just kidding. Don't shut up, Mike.
Turn them in both, it's worth it.
You go, okay, if you do 47, you can, I'll give you the hints, but I think it's a Henry's
Can we
law
get 20
problem.
extra credit?
Yeah, you could get 10 there, and 10 for that one.
What?
And then, what are you whatting?
A 30-point assignment.
Yeah.
I like it.
Oh, I thought you were gonna say, I already got enough points, I don't need any more extra credit.
I'll take all the points I can get.
So this, so this is actually 47, and it doesn't look all that daunting. It just talks about, we're going to use Henry's law, where solubility is a function of the pressure of the gas over the headspace, and here they're giving you, anyway. So just read it. I think so, but feel free. And we are going to talk about Henry's law later this week. So. And then this one, these are due for regular credit, all right? So it's 51, 52, does that sound right?
52 and 55?
Yeah, see, 52 actually refers to 51, so, but 51's not listed, so I don't really understand. So I had to put them both here. So if there's 52, and notice it gives you, we've got two components, and they're both volatile. I think it's very similar to what we did on as our example. Okay?
So we need to do 51 then.
Yeah,
Okay.
I think so.
Yeah.
Yeah,
Yeah.
I think you have to do both of them to do. So you're not getting off that easy. Yeah, I think it's something very similar. There's Raoults law. Okay, and then this one you also have to do for regular credit. This one's kind of. To get the mole fractions, remember that we did it, you're going to have to do another one for the other assignment where you have to get the mole fraction from density and volume. And so this one actually, you're going to have to get mole fraction in an interesting way where it's given weight percent. We also are given the formulas for the two volatile substances. Notice I abbreviated styrene as STY and ethyl benzene as ETB. So, but I think otherwise it's kind of very similar. And is this the last one? Okay, so this is the last one you can do for 10 extra credit points. You can do the first one and this
You also
one.
need 51 for it, too.
Yeah. Yep. And I'm not sure why that disappeared. I don't know. So I'll try to give you both of those hints. That's all the hints I have for that one. And like I said, in my notes, I came up with 3 equations, 3 unknowns, so I don't know.
So the exam is not this Thursday, but next Thursday,
Yes, the exam is a week from Thursday.